Hello everyone and welcome to the IDS Vision channel. My name is Boris Duché and I work in the product management team at IDS as a senior manager in strategic business development. And I'm very happy to have with me today Thibaut Willeman from IDS. Thibaut, would you introduce yourself?
Yeah, so I'm Thibaut Willeman. I work at Prophesee and I'm in charge of the product development here at Prophesee and happy to join here.
Okay, I will start with a small and short recap of the event-based sensing technology, especially comparing it with the conventional frame-based technology. I guess most of you attending to this Vision Channel event are comfortable already with the event-based concepts, yet we have also some newcomers to this event. So before talking about the event-based technology and concepts, we need to get comfortable with the conventional frame-based imaging technology. With a conventional machine vision sensor, it's very similar. It's actually the same kind of technologies and consumer camera. You have an image sensor which is made of pixels, and each pixel is sensitive to light. When a light beam activates a pixel, it will generate a value. On a color image sensor, you will activate not one but three different values corresponding to three different channels for three different colors, the red, the green, and the blue. Depending on the value of each channel, you will generate a color that will be later restituted on the screen of your monitor or your projector. In that case, I'm looking at a green pixel, so the green value is obviously higher. If I look at a brown pixel, the red value will get higher. On a single image, single shot photography image, that will generate for a 4K image sensor roughly 25 megabytes of data, considering that each channel of the pixel is encoded in 8 bits, which is pretty standard, especially on consumer devices. When working with an industrial camera, you usually have the choice or the option to increase what we call the bit depth, which means instead of using 8 bits per pixel, you will encode the data with 10 or 12 bits per pixel. Obviously, the more bits per pixel, the more bandwidth you will use. So that is for a single shot image camera, let's say. Now, what happens when you want to record a video? A video camera is actually nothing more but a still camera, but we take images in a sequence at a given speed. What is pretty common nowadays, it's 60 Hertz, so 60 images per second. You display these images at the same frequency and it gives the impression of a video. But it's basically a sequence of still images acquired and displayed at a given speed. So in here, I reduce the frequency at which I display the video, but you get the impression of a video, even though it's only a sequence of images displayed at 4 Hertz in that case. Question is, when you want to do some machine vision algorithm, how much data is that to process? In 4K 60 Hertz, if you do not compress the video stream, that would be 1.5 gigabyte of data. Once again, considering each channel of the pixel is encoded with 8 bits per pixel. So if you want to increase the bit depth and thus the dynamic range of your system, you will significantly increase the amount of data to process. Nowadays, it's important to understand that you don't find very advanced live video processing algorithms, not because we are limited in the data acquisition from the sensor side, but because we are limited on the resources available on the host side. So to process live video at high frequency consumes a lot of resources. And that's where we see a lot of advantages for event-based sensing. So let me explain in a few words the concept behind this technology from Prophesee. The sensor output is not anymore a 2D image. The sensor output is a continuous stream of events, and an event is a tuple where you will have the position of the pixel that is activated. A pixel is activated only if there is a light intensity change visible, so the light is increasing or decreasing. Basically, that means movement. And each pixel will be encoded. Each pixel generating an event will be generating a tuple with its position, its polarity, which means light intensity going up or down, and a timestamp so that you can very precisely know in the time domain when the event occurs. Important to understand that the pixel activation is asynchronous. On a frame-based camera, all pixels of the sensors are active together at the same time with a global shutter sensor or with a slight delay, line per line, with a rolling shutter camera. Anyway, you don't have the choice. All pixels of an image sensor on a conventional sensor are sensitive to light. They are activated synchronously. With the event-based technology, pixel activation is asynchronous, which means one pixel can be activated independently from its neighbors, let's say. There is no concept of exposure time with an event-based sensor, so a pixel is activated or it's not activated. And with this technology, the dynamic range that you can achieve is very, very high. It's 120 dBs. I think we sometimes communicate up to 140 dBs, which is nothing to compare with a conventional frame-based sensor. The photo response curve on the event-based sensors is logarithmic, while it's linear on a conventional frame-based sensor. So the main advantage of this technology would be the time resolution. On a conventional frame-based sensor, you acquire a sequence of images over time. If an event occurs, if there is movement between the acquisition of two consecutive images, this event will not be available. It will not be recorded with the frame-based camera. What you can see in this video, with an event-based sensor, you continuously acquire events over time. Therefore, you increase the time resolution of your system. And I will now head over to Thibaut, who will give you some insights about some use cases. But first, a very important topic for our customers nowadays, the licensing model of Prophesee SDK.
So we have announced very recently the launch of the Hearth platform. So it's a full stack development platform. And basically, it will replace the current SDK and also go further. So MetaVision SDK will not be available any longer. But don't worry for current customers. The one who bought the SDK since the announcement will get a free migration to the new platform, and there will be a preferred price for customers who bought the 5.2 SDK onwards to migrate to the new development platforms. And this new development platform will enable us to develop as you did with the current SDK on computer, but it will also help to develop on the NVIDIA platform for embedded usage. As Boris mentioned, the advantages of event-based camera is really to have a low data throughput, and so it enables the embedded processing, and NVIDIA for industrial NVIDIA processing and having a local and edge processing is very key. So yeah, that's something we want to enable in this. And regarding the licensing model, it hasn't changed. It hasn't changed. So basically, we want to have a development license where you use the Hearth to develop your use cases. So you will have algorithm available to assemble and to develop your own use cases. And afterwards, once you have developed your own use cases and you see the interest for your manufacturing applications or other applications, there is a commercial license per year and per camera, and depending on the use case and the volumetry, obviously. But yeah, it's a runtime afterwards, and that's how the licensing is working. Regarding the use cases, I took some example here to give you an idea of what we can do. Obviously, the first one we thought about is particle size monitoring and distribution. So here is a free fall of particles. Obviously, it has been slowed down. You can imagine with a standard camera, as you saw before, you see the particles falling very fastly. And with the event-based camera, you have the ability to see very slowly. So the timestamp Boris mentioned earlier is at the microsecond. And so we can have an equivalent up to 10,000 frames per second. So that's very high speed and still very low data throughput compared to standard cameras. So it enables, as you see on the presentation here, to have the ability to see very slowly the particle falling. And here we are tracking the size of the particles, and we can have a live distribution of the particles, which could be useful in manufacturing of grain, flour, also for pet food, for instance. So there is lots of application in those. Second use cases, and that's from the high dynamic range, is when you're doing some welding and there are some welding spatters. With our camera, as Boris mentioned, we are tracking changing lights, but we don't care if one part of the camera is very light and one part of the camera is very dark. So we have the ability to track changing lights from something that is very light, so welding spatters, and we can, and even if it's darker on the rest of the scene, it doesn't care for us. So here it's the use case on where you see the spatters. So we are using the ability to track very fastly those spatters and also the dynamic range. There are also some use cases when you want to track the chord of weld to monitor the heat dispersion. Here it's also another use cases for the camera. It's and we are leveraging again the high FPS equivalent. It's when you have a plastic film manufacturing, and it can go up to tens of meters per second when you process the film. And here we can have a camera looking at the film itself and detect some defaults on the film and prevent the film to break and to stop the manufacturing line if you detect the defaults early. And here again, the advantage of the camera is the high dynamic range, but also the speed of it. And with potentially the NVIDIA embedded possibility with Hearth, you could envision a local processing and to have very high response to your defaults online. Another use cases which leverage the speed is to monitor cable manufacturing, and here you can see if there is defaults in the cable, in the yarn, and typically those process are at tens of meters per second. And with standard cameras, or even with high-speed cameras, sometimes you're struggling to be able to monitor the defaults in the yarn and in the cables. And we've seen with our customers that this is the event-based camera are very suitable for these use cases to detect any defaults on the cable. And that's also some algorithms that are available right now in MetaVision, and we'll include them in the next Hearth platform. And one last use cases that we have developed also, it's surface inspection. So basically, you have a tray where you put a piece. Here it's a piece in leather. And we want to reconstruct the surface to be enabled to track if there is any default. So we see here we have reconstructed the surface, and you see there is a scratch. There are two main holes, but also with some machine learning algorithm which require a bit of training. But then you are able to detect any hole or defaults that you see in here. And for quality monitoring of surfaces, you can think about automotive parts, leather parts for luxury potentially. There is lots of application in those, and that's all what will be available in Hearth. There will be many more, but I wanted to give you a hint of what will be available in there.